When we are interested in the dynamics of a rigid body, and on this rigid body there are forces acting upon it, but maybe even torques, and these forces may generate moments, there are two fundamental equations, which are vector equations. The equation related to the forces and also the equation related to the moments. Now, the equation of forces has to do with the summation, the total forces acting on the body, and I will indicate it like this: a summation over j of the forces Fj. So this is the jth force Fj. The total forces, the sum of the total forces, is just equal to the integral of the acceleration of the single point of the rigid body, for example this point, and we have to integrate over the mass of the body. This will result in the following. So we can also rewrite it as the mass of the body times the acceleration of the center of mass. Let's say that here we have g, the center of mass. So when we consider the sum of all the forces, this summation will produce an acceleration in the center of mass. But if we want to determine completely the dynamics of a rigid body, we also need to consider moments, because moments are related to rotations of the rigid body. And in particular, I will indicate it like this. So the total moment m, calculated with respect to some point O, this is by definition an integral of OP, the position vector OP. So let's say that we have fixed a point O here, and we want to determine the moments with respect to the point O. We have to take the cross product with the acceleration vector AP and multiply by the infinitesimal mass dm. Now this formula can be rewritten. We want to rewrite this formula in terms of something that we know. So for example, the one above was quite simple because we can see straight from the formula that we can rewrite this integral like this, and this is more useful than this formulation here. So the aim of this video is to show you how you can manipulate this expression in order to rewrite it in terms of more familiar terms. Now, I will show you the steps. The acceleration of the point P can be derived from the velocity, because this is the derivative with respect to time of the velocity of the point P. And the velocity of the point P can also be rewritten by using kinematics. We know that we can rewrite it as the velocity of another point. So now let's assume that the point O is a point of the rigid body. So I'm going to rewrite this formula like this. So let's assume here that we have some point O which belongs to the rigid body. In this case, we can rewrite the formula like this: VO plus omega cross product OP. So when we take the derivative, we have the acceleration of the point O plus omega dot cross product OP plus omega cross product the derivative of OP. We already have a formula for the derivative of the vector OP, if you recall, but in general, this is just the velocity of the point P minus the velocity of the point O, which is none other than omega cross product OP. We can also rewrite it like this. So here we have AO plus omega dot cross product OP plus omega cross OP. We can rewrite it like this. And this formula here can be manipulated further, because there is a formula for the double cross product here. And you can find it if you use, for example, index notation. If you use the index notation, you can rewrite the cross product by using a Levi-Civita symbol, and you can do something similar for this one. Then you will get a product of Levi-Civita symbols, and you can manipulate it further. So you can split this term into two terms, and I will give you the result. So I'm not going to derive it, but I have done something similar in previous lectures, so you might need to check those lectures out if you want to understand how to rewrite this. But it is a simple formula. You can derive it if you know very well the Levi-Civita symbol and how to write the cross product in index notation. So here you have equal to AO plus omega dot cross OP plus, and here you have omega dot product. So this omega must be dotted with this vector. So we have omega dot OP, and this multiplies the second vector that we have here, which is omega in this case. It's still omega. And you can see that this is still a vector because we have a scalar. So this is a scalar here, but we multiply the scalar by a vector, so we get a vector. And then we have minus, and then we have the dot product between these two vectors. So we have minus omega squared times the third vector, so we have OP. So we can rewrite the acceleration of the point P like this. And what I want to do is substitute this expression in here. So the moment, the total moment with respect to the point O can be rewritten as integral OP cross product AO. I'm substituting this expression here, remember. Then I have plus, and I have OP cross this. And I can use a similar formula to the one that I've used here. So I have OP squared omega dot minus OP dot product omega dot times OP. So this was just OP cross omega dot cross OP. And you can rewrite it like this. Plus, then here you have OP cross this. So you have omega dot OP, OP cross omega, which you can also rewrite as minus omega cross OP due to simple properties of the cross product. And then finally, I have OP cross this. But you can see that OP is parallel to this vector here. It's very easy to see because we have a scalar that multiplies OP. So when two vectors are parallel, they will give you 0 in the cross product times dm. And so now I can rewrite it like this. I have equal to, I can integrate this. That's just the mass of the body times OG cross product AO. So I can integrate this one very easily. This is just a constant for the integral, so I can integrate OP. Plus, and then I have integral OP squared. I can rewrite it like this. I multiply by the identity matrix minus OP. So I'm going to rewrite it. I'm going to rewrite this like this. OP tensor product OP. And then here I have dm, and I can put omega dot outside of the integral here. We have already done something like this in previous lectures where I have written something similar in index notation, and then we realized that we can rewrite that by using a tensor product. So it's very similar, and I'm not going to do all the details here. But take a look at this. What is this? This is simply the inertia matrix calculated with respect to the point O. And then here I have plus, and I'm going to rewrite it like this. So I have omega cross, and then I have integral, and I'm going to rewrite the expression above like this, minus OP tensor OP dm times omega. So how can I do this? Well, let me do it in red below. So the formula here can be rewritten like this. I have minus because I can rewrite the cross product by switching the two vectors and changing the sign. And therefore I have minus omega cross. And now I'm going to put the scalar before the vector OP. So I have omega dot OP OP like this. And Now, if I use index notation, I know that I can rewrite this as OP tensor OP applied to omega. So that's why I have a term like that, because remember that I also have to integrate over the mass. And one last step is this. Now, consider this fact. If I put another quantity inside this integral here, of this kind, OP squared times the identity matrix, then I'm adding just a zero vector, because omega cross product with this matrix that multiplies omega will give you 0, because when I multiplies omega, you get omega, and OP squared is just a scalar, so it's a vector that's parallel to omega. So when you take the cross product between those two, you will get 0. So I can also add inside the integral this term, and you get the idea, because in this case I will get another inertia tensor. So finally, I can rewrite MO like this. MOG cross product AO, acceleration of the point O, plus inertia tensor evaluated with respect to the point O times omega dot, plus omega cross product inertia matrix calculated with respect to the point O applied to omega. So this is a very important formula, and we are going to use that in a subsequent problem. Now, just take a look at this. If you choose G as the point with respect to which you calculate the moments, so if you choose G, then this vector here will be GG, and that will be equal to 0. So this will become the 0 vector in that case. And the formula will simplify to this: mg equal to ig omega dot plus omega cross product I, so it's the inertia matrix evaluated with respect to G, times omega. So this is a very general formula. It's a very important formula in dynamics of rigid bodies, which generalizes some formulae that you might have encountered in simpler classical physics problems.